Okay, so let's continue with our lecture on first order differential equations. We've covered a couple of methods already: separable equations, linear first order equations, and then our last video we looked at exact equations. Here we want to take a look at miscellaneous, if you like, methods, which I title substitutions and transformations. So basically, the idea is that there are differential equations which don't form into the categories we've looked at already, but you could transform them, okay? Make a substitution, transform them into one of the forms that we know how to solve, like separable equations, linear equations, exact, and so on. So these are the things we want to look at. So we'll look at equations known as homogeneous equations. We'll look at equations of the form dy dx is equal to gax plus by, that is g as a function of this. And then we'll look at Bernoulli equations, okay? So that is a plan for this lecture, for this video. So consider a differential equation of the form here. Dy dx is f of xy. It's a first order differential equation. If this function here can be expressed as a ratio y over x alone, then this equation is said to be a homogeneous equation. Okay, in other words, this right-hand side here can be expressed as a function of just y over x. In other words, every variable there can be expressed in this form. If that happens, then we say that this equation is homogeneous. Well, one of the ways you can actually test, a very simple way you can test homogeneity is that you can pick this, the right-hand side function f, and wherever you see x, replace it with xt. T is some variable, and wherever you see y, replace it with yt. If you do that and you are able to show that f of xt yt is equal to f of xy, then the differential equation is homogeneous. Okay. Now note that the word homogeneous will appear again when we are dealing with second order equations. Okay. So note the context in which it is used here. This is used for first order differential equations. Okay, good. So what is the procedure? Suppose that the differential equation is homogeneous. What is the solution approach? Now, this is what you do. Now, if you can express the right-hand side as a function of y over x alone, then which means we can write it as this: g, a function of y over x, right? Because you can express basically every variable in this form. So what the next thing you do is that make a substitution, right? Let v be equal to y over x. Then, of course, if this is v, then of course it means the y dx is equal to g as a function of v. All right. Because v is equal to y over x, it also means y is equal to v times x. And we can differentiate this using the product rule, right? If you differentiate this, we're going to get dy dx plus, if I differentiate x and leave v, I get this, plus I leave x, differentiate v, I get dv dx. But dy dx is g of v, so I get g of v here. Okay, basically, from these two expressions, right, I can take v to this side, then I can separate variables. Okay, so let's see how we do that. When v goes to that side, I'm going to have x dv dx is equal to g of v minus v, which means that, you know, I can bring the x's to this side and divide through by gv minus v, and I get this. So I have separated variables. That is the point of this procedure, right? The point is that we can't solve the original equation, but we can transform it by making the substitution v is equal to y over x. So now that we have it separated, we can integrate both sides of the equation and we'll get this. Once we are able to integrate this, we're going to get v, and once we get v, we'll get y, which is the solution to our differential equation. Okay, so basically this is the approach, the solution approach to solving homogeneous equations. Great. So what I'll do is do a couple of examples to illustrate how you apply this. So this problem says determine whether the differential equation is homogeneous. If it is, then solve it using the method of homogeneous first order differential equations. In other words, the method we just looked at. So dy dx is equal to y squared all over xy plus y squared. Okay. So how do we do that? First, let's I mean, if you could just express this is equal to, if you like, every variable there can be expressed as y over x. If you can do that directly, you are free to do that. Or you could use the test that I showed before. So replace every y with y times t, every x with x times t as well, and see that the result is actually equal to f of xy. So that's what I'm doing here. F of xt ty is equal to this. So whatever I see y, I replace it with some ty. If you do that, see that now the t's cancel out, right? I can pull out t squared here and cancels this. I'm left with y squared over this, which of course is equal to f of xy. So I've shown that f of xt ty is equal to f of xy, which means that this equation is homogeneous. Okay, good. Now that we know it's homogeneous, it means that we can actually express this as a function of, y over x alone. Of course, here what you can do is that, you can divide the numerator by x squared, right? And the denominator by x squared. And then you can express every variable there in terms of y over x. So when we do that, this is what we get, right? We have dy dx will be y over x all squared. I have y over x here plus y over x squared. All right. So what I've done is here, I divide all of this by x squared. So I'm going to have y over x, everything squared. You do the same thing here. All right. If you divide this by x squared, this x cancels one of the x squared. So you are left with y over x here. And this would, of course, just be y over x, everything squared, right? So that is what we have here. Now that you have it in this homogeneous form, if you like, you make a substitution for y over x. So let v be y over x, which means that the x will be equal to wherever I see y over x, I replace it with v. So I have v squared over v plus v squared. Okay. Once again, because v is equal to y over x, it means y is v times x, right? And then I can use the product rule to differentiate this. So from here, dy dx is actually equal to v plus x dv dx, and that is equal to this, right? This is also dy dx, so I equate them. So x plus v dv dx is equal to, know that I can cancel out one of the v's, right? And have v over 1 plus v. So of course, I can take v to that side of the equation and then try to separate variables. So I take v to that side, I simplify it, I get minus v squared over 1 plus v, okay? So I can separate variables by bringing the v's to this side, right? I can leave the negative here. I bring 1 over v, I bring 1 plus v all over v squared to this side of the equation, integrate with v, take x to that side, that is just 1 over x, right? In any cases, it's algebraic, right? You can do this. So you can separate variables and you get 1 plus v over v squared dv is equal to negative integral 1 over x dx. Good. And from here, I mean, you can use all the techniques you know about integration to solve it, right? This is no longer, if you like, differential equations. So this is the same as 1 over v squared plus this is just 1 over v. The v is equal to, we know how to integrate 1 over x, is just ln x plus your constant of integration. Okay, this is the same as 1 over v squared. 1 over v squared is the same as v to the negative 2, so it's easy to integrate it. You get negative 1 over v. If you integrate 1 over v, you get ln v, right? And it's equal to the right-hand side. Good. Now from here, I mean, you could try to do all kinds of things, but one of the easiest way to do it is that put back v in terms of y over x, right? We know v is equal to y over x, so put it back in here. When you do that, you're going to have negative x over y, right? Plus ln of v is y over x is equal to negative ln x plus c. Remember that ln a over b is the same as ln a minus ln b. So that is what I'm doing here. This can be written as ln y minus ln x, which is equal to negative ln x plus c. Note that this negative ln x cancels out this negative ln x. So you simplify it. And then you get minus x over y plus ln y is equal to c I mean, you could leave your solution as this, or you can multiply through by y, you get this. You can bring the y's to one side. No, I mean, you can take x to that side, and you have y along y is equal to cy plus x. In any case, I mean, you could leave your solution here and it's still fine. So you get an implicit solution, which is given by this as a solution to the differential equation. Okay. In any case, the main technique for solving homogeneous equations is you want to, once you determine it's homogeneous, of course, all you do is that make a substitution, v is equal to y over x, or z is equal to y over x, and then go ahead to try it, to solve it. Okay, good. So you could try this problem that we just did and see whether you'll be able to do it. Okay, good. This says solve the differential equation that, okay, now it is put in a form that looks like, you know, it's exact, but you can check. If you check, you know that you'll find that it is not exact, right? If you differentiate this with respect to y, you're going to get 2y minus x here. And if you differentiate this with respect to x, you're going to get 2x. So they are not equal. So this is, of course, not exact. So you could try to put it in the form of, you know, in the form dy dx is equal to some stuff, right? And see whether it is homogeneous. So that is what we're going to do here. So we can rewrite this as dy dx is equal to, I'm taking this to that side. There's a negative. So I have xy minus y squared all over x squared. That is this x squared. Okay. Now see that this can go in here. I have y over x minus this, and this gives me y over x all squared. So you see that the right-hand side, you know, if you remember the form, the f, right, has all the variables are in terms of y over x. Okay. So straight away, you know that it is homogeneous. Since it is homogeneous, you make a substitution and transform it to a form that you can separate. So let v be equal to y over x, as we've done before. Then dy dx, of course, it will be v. This is v minus this is v squared, right? Once again, because of this, we know y is, you know, x times v. So you can use the product rule to integrate it. Good. So when you use the product rule to integrate this, you get v plus x dv dx is equal to, if you go back, you know, the right-hand side is v minus v squared. So that is what we have here. Okay, this v will cancel out this v, then x dv dx is equal to negative v squared. Okay, so it's not separable. I can divide through by minus v squared, and I take the x to that side, and I get these expressions. Then you integrate both sides. Okay, so I have negative integral 1 over v squared dv is equal to the integral of 1 over x dx. Good. When you integrate this, you're going to get 1 over v, right? Because of the negative, that negative cancels out. And the integral of this is just ln x plus c, which means v is just 1 over ln x plus c. But we know v is y over x, right? Or if you like, y is v times x. So y will just be equal to, I'm just going to take this and multiply by x. That gives me x over ln x plus c. So that gives me the solution to the differential equation. Okay, so that is how you solve that question or that problem. All right. So we have I have put down a couple of problems here that you can try. Solve the following first order homogeneous equations. Well, here it is specified that it's homogeneous. So I mean that's easy. So you just try to put it in the form of y over x on the right hand side, and then, you know, do the substitution and then work it out. Okay. So I'm going to be giving you these as tutorial problems as well. So you want to try your hands on some of these beforehand. Okay, good. Let's move on to, we've done, you know, just a few minutes. So we can actually tackle this, and then the last one will be Bernoulli equations. So we want to look at equations of this form. dy dx is equal to g as a function of ax plus by. Okay. And then if there is, I still have more time, I will do this. Otherwise, I will stop and then continue this in a separate video. So let's look at equations of the form dy dx is equal to this. when you have an equation of this form, the procedure is that make a substitution for what the argument, okay? Ax plus by, make a substitution for that. So let's, for instance, z be equal to ax plus by. Of course, once we have this, we can differentiate it. I have the z, the x will be equal to a plus b dy dx, all right? Which means that dy dx is equal to 1 over, well, note this, I want to isolate dy dx, right? So I'm taking the a to this side and dividing through by b. So dy dx is 1 over b, z dx minus a over b, okay? Good. Now we can use this. We made a substitution for this. So this now becomes g of z, right? All of this is z now, which means that dy dx, which is this, okay, will now be equal to g of z, which is that, okay? So then you can multiply through by b, and you have this, take a to that side, and you get the z dx is equal to a plus b g of z. So now it's separable. If you make this substitution, this becomes separable. It is just constant. This is a constant as well. So if you like, the right-hand side is all z, so we can divide through by it and then take the x to this side. So you separate, you've separated the variables, and then you can integrate. So separating variables and integrating, you get this, dz over a plus b gz is equal to the x. So you then solve this. Okay, once you solve this for z, you go back to here and plug your z in, and you have your solution in terms of x and y. Okay, good. So that is the procedure for solving equations of those type. Let's do an example of that. So solve the differential equation dy dx is equal to x plus y plus 2 all squared. Okay, so you will notice that this is different from the forms we encountered already. So what you do is that let's z be equal to what is in bracket here, z be equal to x plus y plus 2, and find the derivative of z with respect to x. You get the z dx is equal to 1 plus dy dx. Of course, this goes to 0. Then dy dx will be the z dx minus 1, okay? So if you substitute your stuff back in, you know that in place of dy dx, I'm going to have this, right? I'm going to have the z dx minus 1. In place of this, I'm going to have z squared because we made a substitution, okay? Then I can take 1 to that side, and I get the z dx is equal to 1 plus z squared. Good. Okay, so now that is here, I can separate variable. I can divide through by this, right? And take the x to that side and integrate both sides. So that is what I have here. I have the integral of 1 over 1 plus z squared. Z is equal to the integral of dx. Okay, now here you have to go back to calculus 2 to see that if you integrate in 1 over 1 plus z squared or x squared, right? You can replace z by x, and then you remember that when you have an integral of this form, this is actually tan inverse of z. Okay, integral of this is tan inverse of z, which is equal to, if you integrate this, you get x plus your constant, which means that z is equal to the tan of the right-hand side. But we know z, all right? We said z should be x plus y plus 2, and that should now be equal to this. Basically, that is the solution. In this case, we can solve for y, so y is just equal to this expression here. Okay, great. So that is how you solve equations of that type. All right, dy dx is equal to g in ax plus by. Okay, so here's another exercise very similar to what we've done already. This says you are given the differential equation this, let v be equal to this, and show that this substitution will result in an equation like this. You solve this equation for v, and then find a solution to the original equation, that is this equation here. Okay, so try it. Awesome, good. So we still have some time. So I'll just tackle Bernoulli equation, all right? And then we'll be done with first order differential equations. So let's look at the Bernoulli equation. If you have a first order differential equation of this form, dy dx plus pxy is equal to p of xy to the n, where p of x and p of x are continuous functions on some interval, let's say ab, and this n here is a real number, then this equation is said to be a Bernoulli equation. Okay, so often you can identify it by this term here, this y to the n term. Okay, know that if that term is missing, if y to the n, if you like, if n is 0, the resulting equation is linear, and we know how to solve that. Okay, so n should not be 0. Also, if n is equal to 1, note that we can combine this term here and this term here and actually separate variables. So again, we don't want n to be 1. Otherwise, it's something that we know how to do. So n is actually either 2 or greater than 2. All right. So that is what we're going to look at. So for values of n, first divide through by. So the procedure is that you want to divide through by this y to the n term here, and then you get an equation like this. Okay. Once you have an equation like this, you make a substitution for this expression, y raised to the power 1 minus n. Okay, so that's what we're going to do. I just repeated the same equation here. So make a substitution for this. So let v be equal to y raised to the power 1 minus n. Then if I differentiate this, I'm going to get dv dx is equal to, break this down, y raised to the power, I have to subtract 1 from this, right? And then, because this is a function of x, I have to differentiate dy dx. All right, I'm using, if you like, the chain rule, right? As well as, you know, the technique for differentiating powers. Okay, so if you differentiate this, you get this expression here. Okay, now I can divide through by 1 minus n, and that gives me this. Note that the expression on the right-hand side, y to the negative n dy dx, is the same as what we have here on the left here, this expression. Okay, so I can basically replace this by what I have here. All right, and note that we said this should be v. So if I do the replacement, the equation now becomes, in place of this, I now have 1 over 1 minus n dv dx plus p of x. Note that we said this should be v. So this is now v, and this is equal to p of x. Okay, if I multiply through by 1 minus n, I'm going to have this equation here. Okay, now if you notice, because 1 minus n is just a constant, right? This is just a constant. So this equation is actually now a linear equation, and we know how to solve linear equations, right? Using the integrating factor. Okay, so that is the point. Once you get here, you can recognize by, if you want, you can make a replacement. You can let this guy be some p1 of x, and this be q1 of x. Then you see that it is exactly in the form of a linear equation. That is what I've done here. All right, so that equation can actually be written like this, and you see that, you know, if v was a y, you know that this is just like the linear equations that we've seen before. Okay, so that is how you transform a Bernoulli equation. You transform it into a linear equation, and then once it's linear, you find the integrating factor, then you solve it, and then you have your solution. Okay, let's do a couple of examples again to illustrate the procedure. So I have dy dx plus y over x is equal to x squared y squared. All right. So how do we solve that? The y squared term should give you an idea that this must be, you know, a Bernoulli equation. This guy, y squared. So what you do is that divide through by y squared. When you do that, you're going to have this equation here. Y to the negative 2 dy dx plus 1 over x, y to the negative 1 is equal to x squared. And then you make a substitution for the y to the negative 1. All right, the term that multiplies your p of x. Okay, so let's do that. So let v be equal to y to the negative 1. Differentiate this, both sides, dv dx will be equal to, I'll have minus y to the negative 2 times dy dx. Okay. Of course, note that this guy here without the negative is what I have here, right? So if I multiply through by negative, I'll have minus dv dx, that is this guy here, plus 1 over x, y to the negative 1 is v, is equal to x squared. So I have that. Multiply through by the negative, and I get this equation here. And now this equation that we have is a linear equation, and the integrating factor, if you remember, go back to the video on linear equations, okay, if you have forgotten. All right. Once it's linear, we can find the integrating factor, and that is equal to e raised to the power minus integral of 1 over x dx. There should be a dx here, okay? And that is e to the negative ln x. Okay, I can take the negative up here, and I have e to the ln of 1 over x. E and ln cancels out, so finally I have my integrating factor to be 1 over x. Okay, now that you have your integrating factor, if you remember the procedure for linear equations, you have to multiply this equation throughout by your integrating factor, right? And then you can rewrite it in the form d dx of my integrating factor times v is equal to the right-hand side. The right-hand side is negative x squared, but if I multiply through by 1 over x, I'm left with negative x. That is why I have negative x here, okay? So now you can just integrate both sides. If you do, you're going to have 1 over xv is equal to minus integral of this, that's x dx, and that is negative 1 over 2x squared plus a constant c multiplied through by x, and you have v is equal to minus 1 over 2 x cubed, right, plus cx. But remember that we made a substitution for v. We said v should be y to the negative 1 or 1 over y, right? Which means that y will be 1 over x cubed plus cx, okay? Well, it appears that I left this negative out, right? So you can, there should be a minus here. So if I multiply the top and bottom by 2, I'm going to get this expression here. Once again, there should be a minus here, and that gives you a solution. Okay, I mean, you don't have to simplify it to this point. From here, you can get a solution. C1 there is a constant. Okay, so once we do that, we have a solution to the our Bernoulli equation. Okay, so basically that is how you solve a Bernoulli equation. If you divide through by the y to the n term, make a substitution for the product of y and the p term there, and then you can transform it to a linear equation and use the technique of linear equations to solve it. That is basically the procedure. Okay, so here's a couple of problems. Find the solutions to the following Bernoulli equations. So here, you are told that it's a Bernoulli equation. You can tell from this, right? The y cubed term, the y cubed, the y squared terms, right? Y cubed term, they give you an idea that this might be a Bernoulli equation. So even if you were not told, right, that should ring a bell. In any case, you can try them. Here are some more exercises or problems you can try your hands on. Determine if the given differential equation is separable. Okay, check whether you can separate it. Some of them are, others are not. And this one says solve the following differential equation. All right, so here you are not told the method to use, so you just have to look at it and try different approaches or different methods of solving it. Great. So this brings us actually to the end of first order differential equations. Okay, the next topic will probably be second order differential equations. So watch out for the video on that. All right, all the best.